Dear friends, welcome to the world class manufacturing design classes.
Dear friends, in the last session we started of the journey to the red X with the definition and quantification of the problem. In this session, we will discuss briefly on distinct DOE tools for successful solution of given green Y.
If you like the classes,
The block diagram in previous slide shows how the DOE tools are linked. To solve problems systematically, however, a more detailed roadmap is needed to guide teams in search for the red X. And in this slide, the block diagram is such a roadmap with a starting point at the green Y and proceeding with the progressive use of each tool in solution tree fashion to distill the red X. It then monitors and controls it with pre-controls. As we proceed along the road to the red X, each step will be highlighted in this block diagram. The start is defining the green Y. Before the start of DOE, it is important to describe, define and quantify the problem, that is the green Y. Has the problem been clearly stated? Has the green Y been defined and quantified in terms of defect levels or field failure levels, cost, safety or environment impact, longevity? Before proceed to the powerful clue generation DOE tools, the pitfalls in the measurement system associated with the products should be highlighted. More frequently than a possible, the red X, that is the number one problem associated with the green Y, is the weakness and variation of the measuring system rather than the variation within the product. The first question that should be asked after defining the green Y are: how good is the measurement system or measurement instrument? What is the variation vis-a-vis the product variation? Whether the instrument accuracy is 5 times than the product specification. Measurement system accuracy is at least 5:1 relative to the accuracy of the product tolerance or specification. Width is necessary for successful solution of a given green Y. Starting at clue generation stage with multivariable analysis to reduce a large number of unknown and unmeasurable causes of variation to a much smaller family related variables containing the red X, that is the dominant cause. It is a graphical technique that homes in on the most likely cause of a problem by eliminating non-contributing causes of variation. If the multiple variable shows that the largest measure family of variation is within unit, the next step would be to plot the exact location of the problem within the unit. This is the best done with the concentration chart, or it is popularly termed as a measles chart. A concentration chart can show either that there is no one specific location with repetitive problems, or there does appear to be a concentration or defects in a particular location. A multivariate study generally determines three major families of variation: time to time, unit to unit, and within unit. But what if the dominant family of variation is already known to be unit to unit? What if in the same run and at the same time there are both good and bad units? Then the multivariable can be bypassed and the component search process begun. Component search is the third of our clue generation technique for talking to the parts. In the case of the multivariate technique and its satellite concentration chart, component search does not disrupt production, nor does it require any depth of technical knowledge of the product. It can therefore be taught to and practiced by the line operators with less than 1 hour of coaching. Further, the sample size is unbelievably small, 2 units, one good and one bad. As we stated that whenever there were good and bad units being produced at more or less the same time, the multivariate could be bypassed and component search could be used instead. But that what if one of the prerequisites of component search, that both good and bad units must be capable of disassembly and reassembly, is not met? What if disassembly damages, destroys or radically changes the good and bad units, then component search is not the answer. Fortunately, the fourth clue generation technique for talking to the parts can be employed in such circumstances. It is paired comparison. Like the three previous techniques, it does not disrupt production, and its methodology is based on an extremely simple arrangement of data on 12 to 16 units. Generally 6, 8 get good units and 6 or 8 bad units in rank order. Yet it provides a high degree of confidence. When a parameter or quality characteristics associated with the unit is declared to be important. Fifth of our clue generation techniques, product process search, is the latest technique developed by the Shannon and constitutes another breakthrough in problem solving without disrupting a process. Just as paired comparison separates important product parameters from unimportant one, product process search separates important process parameter from unimportant ones. It has been experienced that 70% to 80% of chronic quality problems can be solved with one or more of these clue generation techniques, performed either sequentially or simultaneously. These methods also have the unique advantage of not disrupting the production. Sometimes, however, after the clue have filtered out many variables as unimportant, they may leave 2 to 10 or even 15 important variables, require further distillation of red X, pink X, and pale pink X, along with quantification of their interaction effects. So, more formal DOE techniques are needed as follow ups, even though they don't require disruption of production. Full factorial DOE is to select two levels for each factor, a high level and low level. Then each level of each factor is tested with each level of all the other factors, creating a 2 to the power n matrix or 2 to the power n combination. If there are 4 factors and 2 levels for each factor, there are 2 to the power 4 or 16 combination, which means 16 experiments. If the full factorial is too time consuming and complex for factors beyond 4, and if the whole family of fraction factorial is too statistically weak, what is the alternative? This is precisely where variable search come to the rescue. It has the advantage of a small number of experiments, a maximum of 26, even for 10 factors, as well as the neat components maximum compartmentalization of all main effects and all second order, third order, and most fourth order interaction effect, as it will be shown later in the session. To reduce a residually large number of causes up to practically maximum 20 from earlier clue generation, DOE technique and distill the red X, pink X, and pale pink X. That is the objective of the variable search. B versus C, an excellent validation technique. A central weakness in all problem solving practices is assuming that an improvement once made is substantial, real, and permanent. The history of problem solving exercises is littered with initial successes followed by failures soon after. No attempt is made to go back to condition before the improvement and see if the problem has been recreated. The best way to confirm the magnitude and permanency of the improvement is to go back to the pre-improvement product or process or method and ensure that the problem has been reproduced. Then switch to the new improved product or process or method and ensure that the problem has been disappeared. Do this at least twice more. It is like turning on a light switch. Turning the problem on, turning the problem off. Turning the problem on, turning the problem off again. Only then can the experimenter develop sufficient confidence about the permanency of the improvement. But that is still not the end of the road. Problem solving and product process characterization must be followed by product process optimization. This means establishing the optimum target value, specification limits, and tolerances for the previously characterized input variable. Scatter plots adopted to achieve realistic specification and tolerances when there is no interaction effect, while response offers methodology to optimize interactions. One of the weaknesses of industry is that the engineers and technicians attempt to control a process by checking the product it produces. That is too late. The clue generation technique of product process search is a DOE technique that can separate important process variables from unimportant ones. Variable search and full factorial take DOE further to distill the important variables and their interaction effects. Scatter plots and response surface methodology establish realistic specification and realistic tolerances for each important variables. But all of this work comes to naught if these important variables and their tolerances are not controlled in day-to-day production. Locked up, frozen. We have seen scores of companies where good DOE work resulted in drastically reduced defect levels, only to find a subsequent production that the defects crept back it again. Then procedural plan must be established to ensure that important variables that what characterized and optimized through previous DOE experiments are kept under tight control with a who and how, where and when plan. Process certification, where SOPs are periodically audited for simplification, accuracy and compliance. And at the end, monitored through pre-control charts. These 10 tools are treated in depth in the next sessions, each of which contains a detailed description of given tool and step-by-step procedure and successful case studies. Hope you like this session. Please do comment and make your suggestion. Do subscribe and press the bell icon to get the notification for further classes.